In the previous lecture, we saw how to calculate moments using the definition of expectation. So for raw moments, we use this definition. For central moments, we use this definition here. So when we try to actually calculate the first moment of the exponential distribution, we realized that we had to solve this integral. And it was getting quite messy. It took me around five minutes to solve this. Now that's kind of time consuming. The question is, can we find a solution? Is there a method out there which will help us calculate moments much faster, much more conveniently? And it turns out that the moment generating function is such a tool. Okay, moment generating function will let us calculate moments with much greater ease. Moment generating function is defined as an expectation of this function here, of an exponential function, e to tx. Therefore, to calculate moments, you have to do two things. First, you have to solve this expectation. Second, once you solve this expectation, i.e. you derived the moment generating function, you have to take the derivative of this moment generating function with respect to t and evaluate this at 0. By doing so, you will recover moments. So say if you wanted a third moment, you would take a third derivative of this moment generating function with respect to t, okay? And this will give you third moment. Now, if you look carefully here in this place, you will see that the moments that the moment generating function is recovering are actually raw moments. So they are not central, they are raw moments that we are getting out of moment generating function. In this tutorial, I will just concentrate on this first step, how to get moment generating functions. We said that to get a moment generating function, you need to evaluate expectation of this function. And it turns out that we do it exactly the same as we did for random variables. We plug the e to t times x inside this expression, inside the summation sign. And for continuous variables, we plug it here. And we just evaluate the integral. Okay, so let's proceed swiftly for an example. Let's use exponential distribution. Our task for today is to derive this expression here. And please believe me, this is actually the same as this here, as lambda divided by lambda minus t. Some properties of the exponential distribution: it is defined from 0 to infinity. Okay, it's support of this function. The domain of this function is 0 to infinity. And I also list here some very useful properties without which we can't actually solve this integral. We can't solve for moment generating function. Now, some of them are easy, but let's quickly go through them. The first one is when you have a constant and you multiply it by e to x, you can pull this constant in front of the integral. When you integrate e to x, you get e to x. The product of two e to x's gives you e to x plus y. Then integral of e to ax, where a is a constant, evaluates to this, where the constant comes into the denominator. Yeah. What happens to this expression when x tends to infinity? Well, it also tends to infinity. I put a little table here so you can follow what happens to e to x as x increases. Yeah. What happens when x actually goes to infinity, tends to infinity? Well, e to x tends to 0. E to 0 is just 1. Okay, and here property number 8 is something. It's just for like presentation purposes. You will see that the expression that we'll be getting out of this integral is something like this, and we want to present it more neatly into this format. Okay, let's proceed swiftly with the setup. A moment generating function is defined as an expectation of e to xt, and expectation is just this function times the PDF. Okay, now even though MGF, the definition of MGF is from minus, the limits of the integration are minus infinity to positive infinity, we plugged here 0 because as the lower limit of integration, because our exponential function is defined for all values greater than 0. Yeah, so there's no point of integrating from minus infinity because they're just it's undefined. There's no probability mass there for all values less than 0. Now here I just call with the red here. I call the properties that we enumerated before. So first property is just that you can take the constant outside the integration. Here, property number 3. Follow it closely. It's actually very intuitive. It just says that if you have product of two e2 x's, this reduces to that. Okay, and because we are integrating with respect to x, t minus lambda is actually our constant. So from property number 4, this property here, when we integrate this expression, t minus lambda goes into the denominator because it's like a constant, okay? And our limits of integration are from 0 to infinity, okay? So the question is now, what's going to happen? Obviously, we first take the higher limit of integration. What's happening when we actually evaluate this expression with when x tends to infinity? Well, we can see it from this table. As x tends to infinity, e to x tends to infinity. Well, and then we're unfortunately busted because we can't evaluate the integral simply because the integral would not converge. Okay, so unfortunately, this integral is only defined for values such that t minus lambda is less than 0. Because when t minus lambda is less than 0, as x tends to infinity, okay, the whole expression evaluates to 0. And you can, this comes from property number 6. Okay, so we are done with this limit of integration. Now let's take this limit of integration. 0. What happens if you plug in 0 into the power of the exponential function? Well, it evaluates to 1. It's property number 7. And therefore, our whole expression evaluates to this lambda, negative sign, lambda divided by t minus lambda. And by property number 8, just for presentation purposes, so that it looks neater, and with this condition imposed, we arrive at our moment generating function. Victory, because it turns out that this is exactly the same formula that we specified before as what we were, as our goal was. Yeah, our goal was to get this, and that's exactly what we got. In the next video, we will use the moment generating function to derive the first 4 moments of the distribution, of the exponential distribution. Thank you.